Hello, everyone. So I'm Larry, and I'm going to explain the solution to Yusuko Silver problem milk visits. So on first read, it might seem a bit hard to be able to figure out what the exact path between any two nodes is and whether that path contains an H or G. And it might be very difficult to do that efficiently. So we're going to have to figure out a different solution that doesn't involve that. And the way we're going to do that is we're going to simulate some sample trees, and we're going to be able to find some properties of these paths. So here I've drawn the sample test case. In blue, I've colored the Holsteins, and in green, I've colored the Guernseys. And what you might notice is, let's say you have a path on this graph, like let's say you're on the red path, right? If you're on the red path, then you might notice that you don't have a Guernsey on that path. And what do we notice about this path? Well, we notice that the path only contains edges that go between two Holsteins. And it's very easy to verify that any path that doesn't contain a Guernsey will have to contain only edges that go from Holstein to Holstein, which means if we use a DSU, or if we use some sort of data structure that can essentially store the connected components, or in this case, if we use the red edges, if we store like something that can store the connected components, then if two things are in a different connecting component, that means that you must go through some edge that goes through both H and G to get to that, like to go from point A to point B in two different components. So you must go through both types of colors, I guess, in order to go from A to B if they're in two different components. And so now we've essentially solved the problem because we can just consider all the components. So for example, if we were to create a DSU, that would look something like this, where the first set would contain 1, 2, and 4. That's one component. The next component would just be 3. And the next component would just be 5. And now what you can see is that, let's say you're given a query, like for example, 3 to 5, even though both 3 and 5 are Guernseys, they're not in the same component. And because they're not in the same component, you're going to see both Holsteins and Guernseys on the path from 3 to 5, which means that the path from 3 to 5 will go through a Holstein, which it does. So if you're querying 3 to 5 Holstein, then the answer would be yes or 1. And if you're querying like 1 to 4 and Guernsey, again, 1 and 4 are in the same component, and it's that component is Holstein. So if you look at the path from 1 to 4, this path only contains Holsteins, which means you're not actually looking at a Guernsey at any time, which means that if you're querying for Guernsey, that means the answer would be 0. So from this careful case analysis, we can figure out that the only way for the answer to be 0, the only way for answer to be 0 if and only if the two endpoints are in the same component, A, B are in the same component, and this is important, and the color of A is not equal to X, which is what you're querying. And as long as these two conditions are satisfied, it is guaranteed that the answer is 0. And otherwise, we already know the answer is 1. Because if the color of A equals to X, then already that means that um you're seeing you're seeing the color X right at the beginning. And if A and B are not in the same component, that means that somewhere along the path, you're going to go through an edge that goes between a Holstein and a Guernsey. And as soon as you go through that edge, you are looking at both Holsteins and Guernseys, which means that you are going to be looking at X. Um, and if both of these conditions are true, it's also easy to figure out that the answer would be 0 because if they're the same component and the color of A is not equal to X, that means the color of everything within the component is not equal to X, which means that the path will not contain the color X. So this is essentially the solution. And as I alluded to earlier, you can figure out whether A and B are in the same component using DSU or using some sort of flood fill. Either way, you can pretty easily figure out whether A and B are on the same component using the algorithms I described in the previous lecture. So this problem combines both clever observations as to what the answer would be, and also a clever use of the algorithms that I described. In this case, it would either be DSU or flood fill. Yeah, so that's the solution to the problem. Thank you for listening, and we'll see you next time. Bye.